All right, so for today we are going to be talking about composites again, and we are going to be doing some stress calculations with them. Let's go into it. So let's review just a little bit. So things that matter. So we talked about thermal stress. Remember, stress is equal to your force over your area, and your elasticity is equal to your stress over your strain. And since your stress is force over area and your strain is your change in L divided by L, so they flip-flop. And we also know that change in L is going to equal alpha times L times our delta T. Nice. All right, just for sometimes, if you've looked at other things, sometimes they use delta L. They use a lowercase delta there. It means the same thing, it's just different notation. But anyway, so when we combine all these together, so delta L, so from last time we had sigma is equal to, where is it? Oh, there. E times alpha times delta T, which is wonderful. But what we're going to talk about now is we're going to talk about two materials. Let's, for today, just worry about having them in series with each other. So we're going to have a red pipe here, and that's going to be touching a blue pipe. And they are wedged up in there, right against each other, right against the walls. And if we heat it up, what's going to happen? So things we got to keep track of. This guy has an alpha. This guy has an alpha. They are not going to be the same. We'll call this one alpha 1. This guy is also going to have an E. We'll call that E1. The E1 is not going to be the same as this guy's E. Modulus of elasticity, all that jazz. Now you can look these up if it tells you what material it is, of course, but they're not going to be equal to each other. But the main thing we got to worry about is what is equal to each other here. So are the delta L's going to be equal? No, they're not. Well, I suppose in some ways they would be, but not really here, because what's going to happen is if the blue one expands more, it's going to push the boundary a little bit this way, depending on the values of those two constants there. All right, so things might not be equal every time, but what will match is your force. Now, the reason why is because of Newton's third law. If this guy pushes on a force to the red one, this one will push a force on the blue one. Equal opposite reactions every time. So that's going to be how we hook these together. All right. So solving this guy, let's solve him for force. We find out that force is equal to area times elasticity times delta L over L. Let's just simplify that to strain there. Okay, so this for one thing is going to equal A to E to epsilon 2. All right, now where's the strain going to come from? The strain is going to come from our formula here. Right, so we have to figure out what the changes in length are. But it'll be a little annoying because the changes in length is dependent on temperature and it's dependent on force. All right, let's get into one of them. Maybe that'll help you out. Hopefully, anyways. All right, this is heated from 100 to 200 degrees Fahrenheit. What's the stress? I know, Fahrenheit, but we're okay. It gives us all in English units here. Go America. So we've got aluminum over here. Aluminum's 10 long. We have an A, we have an E, we have an alpha, and we have steel over here. Steel is 15 long, and it's got some different values here. So what we're going to have to do is we're going to have to figure out some calculations here. We're going to be double dipping from one side from the aluminum, one side from the steel for each one. Let's try to keep it color coded here. We'll try to do aluminum in red. So what we first would want to figure out is how much each one wants to change from thermal expansion. So delta L is going to equal our alpha times L times delta T. All right. Now alpha, let's just stick with aluminum for this instant here, is going to be 12.8 times 10 to the minus 6 times the length of 10 times the delta T of 100. Boom, boom, boom. So we are going to get a delta L for aluminum of 0.0128 inches. Nice. So we're going to do the same thing for our steel here. Same formula, just have some different values. So we're going to have 6.5 times 10 to the minus 6 times 15 this time, because it's longer, times 100, because it changes by the same amount of temperature, same amount of degrees here. So steel is going to change by 0.00975 inches. Okay, so far so good. So what we know is the steel wants to expand by this much, right? That's the 0.00975. And the aluminum wants to expand by this much. They're pushing into each other. But it's not going to be a fair fight. Okay? Now, when we're talking about our strains, remember, come from a delta L. So something we know is that the delta L for aluminum from strain, we'll call this strain, plus the delta L from steel is going to equal the delta L from aluminum plus the delta L from steel from thermal. Okay, here's what's happening here. These guys are being compressed by this much between the two of them, and we know what that value is. So we know we can combine these two together, just add them up. We're going to get 0.02255 inches. That's how much they're being squeezed combined, all right, thermally. Now the strain, if we solved it for delta L's, would add up to the same distance because they want to be this length. Aluminum wants to be this length, steel wants to be this length, but they're being squeezed together, and those two changes in length are going to be equal. All right, so now what we have to do is we have to solve for delta L. All right, that's the goal, solving for delta L. So let's figure this out. So let's start from the good old days. We know it's going to have to involve stress. Let's talk about stress. Stress is equal to force over area. So far so good? Yes, we're going to need that, but we also need the other side of stress, because remember E is equal to stress over strain. So we're going to have to say that force over area, bring this over here, is equal to stress or Young's modulus times strain. All right, so we're dealing with this guy here. So strain has our delta L in there, so E times delta L over L. All right, we're solving. All right, so we're solving for delta L now. So delta L is going to equal F times L divided by A, and then the E is going to go down there. And this is going to be what delta L equals. Now this is going to be for aluminum and for steel, so we got to plug them in both together. So we are going to have F times L over A times E. These are all for aluminum. And then we're going to have an identical situation for steel. All right, but there is something they have in common. This F is the same for both of them. These are the same value, right? This is the variable we're going to solve for. So the length, plugging it in here, so F is going to be just F times the length. We know the length of aluminum, it's 10. We know the area of aluminum, it's 2. We know the modulus of elasticity of aluminum, it's 10 times 10 to the 6. 10 times 10 to the 6. Yeah, I know. All right, now we also have for steel, the F. The F is going to be exactly the same times L. The length of steel is 15 divided by the area of steel. Area of steel is 1.5. And the modulus of elasticity is 29 times 10 to the 6. And this is going to equal that number here, so that's the 0.02255. All right, we've got just one variable. We can solve this. We simplify this whole fraction here and this whole fraction here, add like terms together, bada bing, bada boom. F is going to equal 26,000, rounded to 700 pounds. All right, that's the unit because it's force. Force is measured in pounds, and we're in English units here. Okay, so this is the amount of force that's on the system. So if you had to measure how much the wall is pressing inwards, it would be 26,700 pounds. Now, it wanted to know the stresses, okay? So the stresses are going to be different for each one. Aluminum will have a stress and steel will have a stress. Why are they different? Because remember your formula for stress right there. So let's go with aluminum here. Stress is equal to force over area. We know what the force is. The force is 26,700. We know what the area is for aluminum. The area is 2. So that means the stress on the aluminum is going to be 13,300 about. And then we know from steel, steel is going to have the same force, 26,700, divided by 1.5, because it's a little more narrow. And that's going to have 17,800 pounds of stress, PSI of stress. Hey, and that's how you're going to do a problem like this. All right, so the important things are, in review, you have to figure out what's the same. What's the same is going to be the forces, and we can use that to see how the lengths are going to add up with each other. The lengths are coming from the heating, all right? The heating increases the length. The strain is going to decrease the length by the same amount. Solving it using our elasticity formula, this guy here. And then you just solve for F, and then you can find everything from there. All right, hopefully this helped. Have fun with these problems, right?